Okay, so we are talking about integration, and so we've looked at this thing that we call the integral, definite integral, and so we have some function. We integrate some area. We integrate this function between A and B. And so the examples that we've looked at f of x is a positive function. That means that it lies above the x-axis. And when we do that, we see that this thing here can be interpreted as an area. Okay. So here is our A, here is our B, here is our f of x. And we see that when we do this integral, what we're doing is just adding up all these little rectangles. And so it's a limiting process, just like taking a derivative was a limiting process. It was taking kind of a limit of a rise over run. Now we're just sort of adding up lots and lots and lots of little rectangles. Okay? And then when we do the limit, what we're going to do is actually get this kind of actual area here. It's kind of fun. I don't do that. Right. So what we do is the area under the function f of x of the x-axis and between A and B, well, it's between x equals A and x equals. Let's just remember that was. Right, so here's x equals A. It's like a fence. Here's x equals B. So it's kind of like between four. It's like a four-sided area, right? It's not quite a rectangle, right? Three of the sides are kind of rectangular, but the top is given by the function, so that can be quite curvy. Okay, so this is nice. This gives us a really kind of solid kind of way to interpret this integral. Okay, and in fact, I've already given you problems where one of the problems is find that integral, and what you do is you go ahead and you add up all the squares that's inside that area there and try to approximate things that way. So that's a perfectly good way of integrating. And in fact, my PhD advisor, he was a student during the Korean War. He was like an undergraduate student, and he was, I know, he got some work working for the army, finding integrals. And the way that he did integrals were, they got really nice cardboard, and they would draw the function on the cardboard, and then they would cut out this area, and then they'd have these scales that were like chemistry scales, so they were super accurate. And so they would then weigh a piece of cardboard, and obviously the weight of the cardboard would depend upon how much cardboard there was, and that would depend upon how much the area was. And that was the way that the army did integrals back in the 1950s. And so this is exactly, so you can see exactly why that would work. And that was actually not a bad way of doing things, because, you know, they get curves from various things to do with artillery and whatever, and they just have data. So instead of worrying about a function, and that was how they numerically integrate. So I always found that story fascinating. Anyway, so we have a little problem because, of course, functions aren't always positive. Okay, so who's Eric? Are you trying to speak? No, Matt, are you speaking? No? Okay. Okay, so what happens if f is negative? So let me draw a different picture. And it's not a hard problem. So let's say instead of f that we did before.
Hey, Professor.
Oh, yeah?
The framing of your camera is kind of a little close and we can't really see most of what you're doing. We can see about half of it.
Okay. Is that better?
Yeah, that works.
Okay, thank you. Okay. So yeah, so this is what happens when f is positive. So what happens if f can be anything? Okay, so again, we're going to have A, we're going to have B, but now our f could be something like this. Okay, and so we still have f of x equals b, but what do we get? So definitely, so one thing that we can see for free from how we define integral is the fact that if we've got the integral from a to b of f of x dx and integral from b to c of f of x dx, and get the integral from a to c of f of x. And that's going to be true because area is additive, right? So I've got the area up to some point here, and I've got an area from here to here. If I put the two together, I'm going to get the total area. So that's that thing. So what I can do is cut this up into two bits. And if I do the integral up to this point here, I'm going to get that area there. But what happens when I try to integrate between here and here? And I look at this. Well, what am I doing? I'm adding up rectangles, right? So I'm going to get an area, right? But what are the heights of the rectangles? The heights are going to be negative numbers. So what I'm going to end up getting is negative the area here. So what I'm going to end up doing is I'm going to get this area minus this area. So what the actual interpretation of this thing then is the signed area between f of x and x-axis and between x equals a and x equals b. And by signed area, maybe I should put that in. quotation marks. And by signed area, I mean that area above the x-axis is considered positive and area below the x-axis is considered negative. So that's a very easy way to handle that problem. Okay, so let's actually do like an actual problem. All right, so let's have a look at area, the integral -1 to 2 x squared minus 1 dx. Okay. So let's draw and see what it looks like. So x squared minus 1 is a parabola. And let's have a look. It is smiling because that is positive. Its roots are -1 and 1. Right, so when x is less than 1, x squared minus 1 is going to be negative. So it's going to kind of look like this. And then between 1 and 2, it's just going to, well, at 2, it's going to be 3. And at 0, here is -1. Okay, and so if we were to sketch in what this represents, it'd be the area, signed area between the function, the x-axis, and x equals -1 and x equals 2. And so like that. And so what would it be? Well, say this is kind of like a triangle of base 1 and height 3. So this is around 1.5 approximately. This thing here, well, what is it? It's inside a rectangle of a 2x1 rectangle, and so maybe it's something like -4/3, for instance. I can't remember exactly what it is. So if this was the case, then this integral, if these are approximations, would be approximately the positive area subtracted by the area underneath the x-axis, and so we might assume that it's around 1/6, for instance, because a lot of these things will be cancelling each other out.
The area will be negative.
And it, yes, no, I'm going to answer that correctly. An area is positive, but a signed area can be negative. So yes, it's possible for an integral to be negative, but actually this area here is 4/3. I mean, it is what it is, like it's an area, but because it's below the x-axis, its signed area is negative. So that's a more accurate way of talking about it. Okay. So that's kind of the thing. So at the moment, we haven't got great techniques for actually finding integrals yet. We're going to develop that. At the moment, all we're doing is just interpreting what these integrals mean. This is like the same thing we did with derivatives, right? We spent a lot of time figuring out exactly what a derivative was. Then we spent a lot of time figuring out actually how to do derivatives well. And then we spent time figuring out stuff that we can do with that information. We're going to follow the same line here. We're going to figure out what integrals are. We're going to figure out then how actually to find integrals. And then we're going to figure out what we can do with that once we've found it. Okay. So let's give another example of this. So let's have a look at the integral between 0 and 4 of what? X cubed minus 7x squared plus 11x. Okay. So what's this going to look like? So at the beginning, we don't know anything about this at all. So we've got to somehow do some kind of analysis. So one of the things we might do is just kind of like factor it. Okay. Then we've got to figure out, well, what exactly does that guy look like? Okay. Do that. We then go ahead and graph that. It's going to be between 0 and 4. And what happens when we use the quadratic equation on that? The root of that is going to be 7 plus or minus square root of 49 minus 44 on 2, which is 7 plus or minus square root of 5 on 2. Square root of 5 is around 2 and a bit. So the positive one is going to be outside our range here. The negative one is going to be inside that, and that's around 2.38. Okay, so we have a 0 at 0. We have something at 2.38. Okay, and what we would find out that it is positive here and negative here, and so it would look something like that. Okay, so you could have done that like over there. I did a few computations. An easier way to do it is just to use your graphing calculator and see what it's
Did he disappear for y'all, or is that just me?
Sorry about that. I did something. We lost each other for a while. To be able to solve this problem, you've got to be able to find where they intersect, where on which interval G is bigger than F, and on which interval F is bigger than G. So this is actually quite a tricky problem. Okay. So let's do kind of like a more concrete problem. Find area between f of x equals x squared and g of x equals x. And I'm giving no bounds. Okay, so that looks a bit weird. But when we graph it, you'll see that it's not. X squared is what? Just a parabola, right? So it looks like this. X is just a straight line. And it looks like this. So after you graph it, you can see that I don't need to give bounds, right? There's a quite definite area between the two curves. Okay, and so now if I want to write that as an integral, I actually have to find the bounds myself. How do I find the bounds? Right, it's where they intersect. When does x squared equal x? Or when does x squared equal x? What's this one? Point 0. What's this point? What positive number when you square it equals itself? 1. Which function is on top? G of x, it's x, right? So it's x minus x squared. So that's the answer. And actually, that's a pretty subtle little question. So you actually had to understand exactly what an integral was in able to write this down. The next thing you want to do, of course, is to actually find that number. That's what we're going to do later in the course. For the time being, just being able to figure out that this is the answer to this, that's what I want you to understand at the moment. And if you do that, if you understand why this is the answer to that, well, the reason is because of this diagram here. Okay. So, okay, so this is what we did today. Okay, so we started off by just thinking about what we've done the previous 2 days, right? And the fact that the integral of a positive function is the area underneath that graph. And we know the reason why that is so. The reason why that is so is because the way that we find the integral is we just add up all these rectangles here, and those rectangles are areas, and then we set these thinner and thinner and thinner until those rectangles exactly fit into that area underneath the curve. Okay, so that's the thing that should be stuck in your mind, that image right there. Okay, and then all we have to do is make the one modification, and that is when the function is negative, the area is below the x-axis, and we can think of that integral as negative area, sine area. Right? So things above the x-axis get counted positively, and things below the x-axis get counted negatively. Okay, so for example, in this thing here we have a nice function here. Between 0 and 5, its area is 8. So therefore, its integral is 8. Here, now we have a function below the x-axis. Its area here is 6. So therefore, its integral is -6. So remember, area is always positive, just like distance is always positive. It's where you place it that can make it negative. And then the trickier one is right when we have a function like this. Here in the first half, we have a little mountain whose area is 10. And here we have a little valley whose area is 3. So the integral between 0 and 5 then is 10 minus 3, it's 7. Okay? So that's the main little bit that we did today. It's just interpreting what it means when the function is negative. You get this negative area. And then the other bit of useful thing that we did that you're going to end up getting questions on is figuring out the area between 2 curves. Right? So what's going to happen, and what you're going to get is going to be an integral between 2 bounds. So either the bounds are going to be given to you, or if they're not given to you, you have to figure out what the geometry of the curves is to see where there is a region that's been cut off, and that'll give you the bounds. And then this is going to be the integral, and the reason for that is because when we look at the little rectangles, right, we're going to get the base is still going to be dx from that delta x, and the height of the rectangle is going to be the function on top minus the function on the bottom. So it's possible, and I showed you an example where it's possible for that to swap, in which case you'd have to break up the integrals into 2 parts, one where f was on top of g, and the other one where g was on top of f. Right? Because I'm asking for an area, I'm asking for a positive number. So here's a little problem that's going to just illustrate the difference between integral and area. So to be able to make sense of this, we're going to have to draw this function. Right, so x cubed minus x is x times x squared minus 1 is x times x plus 1 times x minus 1. Okay. So we're only interested between 0 and 3. At 0, it's a 0. At 1, this is also 0. At 2, 2 cubed minus 2 is 6. So let's put 6 here. It's here. And at 3, 3 cubed minus 3 is 27 minus 3 is 24. Okay, so at 3, it looks like this. And so this function kind of looks like this. So the total area between x cubed minus x and the x-axis is equal to this. Plus that. So if we call this area 1 and this area 2, then the answer to B, so the answer to A is area 1 plus area 2. Because I'm asking for the total area, and area is additive. The answer to question B, though, this integral is area 2 minus area 1. That's because we're asking for an integral, and in an integral, area below the x-axis counts as negative, and area above counts as positive. And so the answer to question C is no. They are not the same things. And the reason for that is that area below the x-axis is considered differently in these two problems. In A, area below the x-axis doesn't make any difference. It's still area. So it counts as positive. In B, it does matter. Area below the x-axis is negative. And so we subtract it. Okay, so super, super important example this. If you understand this, then you know this section perfectly. This is the problem to understand this section. Okay, everyone's looking kind of confident. That's good. Okay. So here is a function, and here is an area. Which one of these four things gives us this blue area? So everyone have a look. Ellie, what do you think?
Why not? Either C or D.
It's C or D, right? Because you see the bounds -1 to 1/2. Okay, that lines up with that. So these ones are wrong because -2 and 2 is not what the region is. Which one of those is the correct one? What is the function being integrated?
Oh, it's C.
It's C, right?
Yeah.
There's the function There's the function.
I was like thinking probably too hard, I was like writing for
Right.
myself.
This is just some rando function that's walking off the street, nothing to do with this problem at all. Well, actually, it's the derivative of this. What's that got to do with anything? Okay, yeah, C is quite definitely it. Excellent. Okay. Now, typically, it's hard to find definite numbers unless the functions are really simple functions. And this one is simple because the functions are straight lines. So that means the areas are going to be rectangles or triangles. And we know how to find areas of rectangles and triangles. So, which one of those is going to be that integral? Anna, can you would like to make a guess?
Is it B?
B. It kind of looks right. I mean, that's what I would guess without even doing anything, right? Because clearly the answer is positive. So it has to be A or B. And I bet you 19 is the area and 11 is the integral. I just sense that in my bones, and let's just have a look. So this triangle here is base 5, height 6. So that is is it 15? And then this triangle here is base 4 and height 2, so it's area 4, 15 and 4. The area is 15 plus 4 is 19. The integral is 15 minus 4 is 11. So yeah, you were right. Okay, here's another one. So here we have some functions, yeah, and we're interested in the integral between 0 and 10 of that function. So which one of these 5 things do you think has the integral closest to 0? Peyton, what do you think?
C.
C, yeah, because we see, right, it's the only one with positive and negative area, and they look like they can't approximately cancel each other out. So this is definitely positive, 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 negative. So that wasn't so hard. Okay. Here's just another silly problem. So here's some function, and we want to find an integral which is a positive number. And so here we're given some choices of bounds. So which ones make the integral positive? Okay. So what do you think between -1 and 0? Positive or negative? Shake of hand. Yeah, it's negative, right? Because definitely this thing here outweighs that. -1/2 and 1. So between here and here, you think it's positive or negative? Positive, yeah? Because we've got this, and that's going to outweigh that and that. So B is definitely a good one. What about C? Between 0 and 1. Yeah, it's a little bit negative here, but it's definitely outweighed by that one there. 0 and 2. Probably not, right? Because this, I mean, there is a nice big one here, but that's such a thin sliver. I bet that one outweighs it. So I'm not going to have D. And -1 and 2. That's a hard one. You'd actually have to get out your ruler and determine, because you're gonna have that and that and that. And then against that, that and that. It looks like actually it could be like equal, so it looks kind of zero-ish. So maybe, maybe not. So this would be a terrible test question, so I might give it to you.
I think well, it's gonna goes on -1, right? So that's like the whole thing.
Oh, yeah, sorry, right, I did it from a heart. Right, yeah. If it's -1, oh, it is an okay test question, right? From -1 to 2 is definitely going to be negative for those two things. Put it out. And then finally, I think we've just got time for this one. What represents the area of the shaded region? Okay, so there's two things to worry about: the bounds and the integrand. Okay, so what are the bounds going to be? Between here and here, right? So between 0 and 1.5. So definitely we can eliminate A and B. Okay. Which function is on top? So G is, so the answer is D. Okay.
If it's the integral and then have 0 on top and 1.5 at the bottom, what does that mean?
So this would be the area between, I mean, this one here, this would be the area between these things here. So it'd be this area here. It'd be that integral.
I mean, like if it was positive, if it was 0 on top and then positive 1.5 on the bottom, like the A and B got flipped.
Oh, you mean like?
Yeah.
Then that would be like the rectangles having negative width. And so that would be negative of 1.5 to 0. Okay. There we go. See you, Jinro.